Hello friends, welcome in a ROSE project. This ROSE project is conducted by Rayat Shikshan Sanstha's Sadguru Gadge Maharaj College Karad. Myself Radhika Pawar. My subject is physics. In last lecture we already start chapter number 4 thermodynamics. In last lecture we see the basic concepts of thermodynamics, zeroth law of thermodynamics, and in this lecture we see the first law of thermodynamics, thermodynamic state variables, thermodynamic equilibrium, thermodynamic state variables and equation of state, and next is PV diagram. Here, first law of thermodynamics. The first law of thermodynamics gives the mathematical relation between work and heat. The first law of thermodynamics is based on the law of conservation of energy, which states that energy cannot be created or destroyed but can be transferred from one form to another. In 11th standard, we see the law of conservation of energy. We all are know the law of conservation of energy, which is the energy can neither be created nor be destroyed, but it can transfer from one form to another. The energy can be transferred from one to another form. Consider a thermodynamic system which consists of an ideal gas enclosed in a cylinder with a movable, massless and frictionless piston. Here consider a cylinder which consists of a gas, and this cylinder is provided with movable, massless and frictionless piston. Here the gas in the cylinder is a system, and cylinder along with piston is its environment. Here consider the work done by the system in increasing the volume of a cylinder. Here work done by the system means here work done by the gas to increase the volume of a cylinder. Therefore, during this expansion, when volume of the cylinder is increases, therefore there is a expansion. During this expansion, as shown in figure, gas molecules which strike the piston lose their momentum to it and exerts pressure on it. As a result, piston moves through a finite distance. Here, the gas molecules strike the piston and therefore lose their momentum, and piston moves through a finite distance. Therefore, here the gas does positive work on the piston. Here gas does a positive work because here for during the expansion the gas molecule loses its energy, therefore internal energy decreases, but here is work done is positive by a system. Next is when the piston is pushed in so that the volume of a gas decreases. Here piston is pushed in. Here when piston is pushed inside a cylinder, the volume of the cylinder is decreases. Here gas molecules of a cylinder are moved with a cylinder, and there is a compression in the system. Here the gas molecules gains the momentum from the piston, and therefore their internal energy of the molecules is increases because here volume of the cylinder is decreases during compression, and gas molecules gains the energy from the piston, and therefore the gas does negative work on the piston. Here internal energy of a system is increases and work done is a negative. Consider a figure C. Here in this figure we shows that a gas enclosed in a cylinder with movable, massless piston and frictionless piston so that its volume can be changed. Here piston is provided to the cylinder, therefore the volume of the cylinder can be increases or decreases. Therefore, let the A is the area of cross section of cylinder, P is the pressure exerted by a system on a piston, Therefore, F is the force exerted by a system on a piston. Therefore, force exerted is equal to P into A. Here P is the pressure and A is the area of cross section of a cylinder. Here F is equal to P into A. When piston moves through a distance dx, then work is done. Here the piston is moves from the x to dx. Here the distance change in distance is a dx. Therefore, F dw is equal to F into dx. Here dw is equal to F is equal to P into A. Therefore, dw is equal to P into A dx. Here dw is equal to P into dv. Here A dx means the change in length, therefore change in volume of a cylinder. Therefore A dx is equal to dv. We can write A dx is equal to dv. dv is the change in volume. Therefore dw is equal to P into dv. Let Vi is the initial volume and Vf is the final volume. Then the integrating equation, above equation, to the limit Vi to Vf, we get a total work done. Therefore, W is equal to integration Vi to Vf, P dV is equal to, P is constant, therefore integration of dV is equal to Vf minus Vi, therefore W is equal to P into Vf minus Vi. This equation gives the amount of work done in changing the volume of a system. Here, for change the volume of system, the amount of work done is equal to P into Vf minus Vi. Here Vf minus Vi is the change in volume from initial state to final state. Here, when the amount of heat Q is added to the system does not do any work, but its internal energy increases by the amount du is equal to Q. Here we see when the amount of heat, Q amount of heat is added to system and system does not do any work. Therefore, by adding the heat into the system, the internal energy of the system is increases, and this increase in internal energy du is equal to Q. Here internal energy is denoted by U and du is the change in internal energy. Here, on the other hand, when the system does work to increase its volume and no heat is added, the system loses its energy and internal energy decreases. And other hand, when system does work and there is no any amount of heat is added, therefore the system loses its energy and this internal energy decreases. This means that W is positive and du is negative. Here work is done but internal energy decreases, therefore change in internal energy is equal to negative and vice versa. Here the W is positive, W is negative, or du is positive, du is negative. Therefore du is equal to minus W. Change in internal energy is equal to minus W. In practice, the internal energy can change by both ways. Therefore, internal energy changed by adding heat or doing work on the system, or internal energy is changed by adding heat and do not do any work on the system. Therefore, du is equal to Q minus W. Here Q is the heat and W is the work done. And this is the mathematical equation of first law of thermodynamics. Here we can rearrange this equation. Q is equal to du plus W. Also, this is also mathematical equation of first law of thermodynamics. The quantity W means work, Q means heat, is positive, negative, or zero. Therefore, change in internal energy du can be positive, negative, or zero. This change in internal energy or work and heat is positive, negative, or zero. This we can explain this by the case first, case second, and case third. In the case first, when internal energy is positive. In the case second, when internal energy is negative. And by case third, when the internal energy is zero. We see the case first, where the internal energy of a system is increases, therefore the internal energy is positive. If the figure A shows that when more heat is added to the system than the work done by it, therefore in this case the internal energy of a system is increases. Here heat is more heat is added in the system and work done by the system is less than heat added. Therefore in this process the internal energy of a system is increases. Therefore du is equal to q minus w. Here q is equal to du is equal to positive. Therefore the increase in internal energy du is greater than 0. Here the change in internal energy is positive. In case second, the figure B shows the case second. Here when more work is done by the system than heat added to it. Here work is done by system is more than heat added to it. Therefore the system loses its internal energy and the internal energy is negative. Therefore internal energy is less than 0. In this case the heat added is less and work done is more than heat added. Therefore the system loses internal energy and internal energy is negative. In case third, here the system heat added in the system and work done by the system is same. Therefore there is no any change in internal energy of a system. Therefore change in internal energy is equal to 0. By these three cases we see that the change in internal energy and heat is positive, negative or 0. The first law of thermodynamics is the extension of law of conservation of energy to a system which are not isolated. Means here a system which allows to exchange energy. Here exchange in the form of work and heat. Here the system energy is exchanged in the form of work and heat. Now let us move towards next point, thermodynamic state variables. Here in last lecture we see the concept of thermal equilibrium. Here when the temperature of a system it changes, then the other properties of a system can also change, and this we understand these properties. First is the property of a system or a system variable. Here the thermodynamic state variables are pressure, volume, temperature, density and mass of a system. When a system at a constant temperature, there is no any change in the system, but the temperature of the system it changes. Therefore the properties of system, that is pressure, volume, temperature, density, mass of the system are also changes, and these variables are called as thermodynamic state variables. The extensive and intensive variables. Here intensive variables do not depend on a size of the system, and extensive variables depends on a size of a system. Here intensive variable of a system does not depend on size of a system, but extensive variable depends on a size of a system. Here thermodynamic equilibrium. Here first we see what is mechanical equilibrium. A system is said to be in a mechanical equilibrium when the pressure in a system and between the system and surrounding is same. When a system is, we can say the system is in mechanical equilibrium when there is no change in a pressure. The pressure of a system between the system and surrounding is same. Therefore, we can say that the system is in mechanical equilibrium. Second is chemical equilibrium. A system is said to be in a chemical equilibrium when there are no chemical reaction going on within the system and there is no transfer of matter from one part of system to other due to diffusion. Here the system, we can say that the system is in chemical equilibrium when there is no chemical reaction is going on or within the system and there is no transfer of matter during the diffusion. Then we can say that the system is in chemical equilibrium. A thermal equilibrium. A system is said to be in a thermal equilibrium when temperature of a system is uniform throughout and does not change with time. Here the thermal equilibrium concept we see last lecture, that is in thermal equilibrium there is a temperature of a system is uniform and there is do not change with time. Temperature of the system does not change with respect to time. Now next point is thermodynamic state variables and equation of state. Here the equilibrium state of gas is completely described by pressure, volume, temperature and mass. Here any system, any equilibrium state of system, we can describe this by using the state variables which are pressure of system, temperature of system, the volume of system and the mass of system. Here a thermodynamic system is not always in equilibrium. This figure shows the equilibrium state. When ball is punctured, the air inside the ball is suddenly expanded to atmosphere. This is not an equilibrium state. During the rapid expansion, pressure of air may not be uniform. Here, when this expansion is formed, when the ball is punctured, there is the expansion of air into the atmosphere. But this rapid expansion, the pressure is not uniform. The various state variables are not always independent. They can be mathematically related. Here the state variables are not independent. They can be mathematically related, and this mathematical relation between the state variables is called the equation of state, and the equation of state for an ideal gas is PV is equal to nRT. This is a equation of ideal gas which is PV is equal to nRT. Here P is pressure, V is volume, N is number of mole, R is gas constant and T is temperature of a system. Here the thermodynamic state variables are pressure, volume, temperature and a mass of a system. Now let us move towards our next point, the PV diagram. Here the PV, what is PV diagram? Here P means the pressure and V means the volume. The graphical representation of the equation of state of a system is called the PV diagram. Here we know that in first law of thermodynamics we give an equation of work done in changing the volume is W is equal to integration VI to VF P dV is equal to P into VF minus VI. Here VF is the final volume and VI is the initial volume. Here VF minus VI is the change in volume and P is the pressure. The above equation can be evaluated if we know P and V, and equation can be represented graphically. This equation, we can evaluate this equation by know the pressure and volume. A gas is confined to a cylinder with a movable, frictionless and massless piston. Can be the gas when is confined in a cylinder, there is a movable, massless and frictionless piston. Then we can expand with a varying pressure. We can expanded gas with varying pressure. We can compress the gas with varying pressure and expanded at constant pressure. Here we see first when the gas is expanded by varying pressure in figure A, the area under the curve in the PV diagram is a graphical representation of the value of integral of equation. First W is equal to P into VF minus VI. Here its volume it changes due to outward displacement of a piston. Here the in last point, first law of thermodynamics, we have seen the volume of the gas is expanded by displacement of piston in outward direction. Therefore, the pressure of the gas is decreases. Internal energy is decreases. Also, pressure of the gas is decreases. Therefore, the pressure of the gas is decreases and work done by the gas is positive. In this diagram, PV diagram, here P means pressure and V means volume along the x-axis and P is along the y-axis. Therefore, here pressure is decreases. Pressure is decreases. Here positive work with varying pressure. Next is when the gas is compressed due to inward displacement, there is pressure of gas is increased. Here the gas is compressed due to inward displacement, therefore the gas in the cylinder is compressed and pressure of the gas is increased. Therefore here work done by the gas is negative and internal energy is increases. Here P along the y-axis and V along the x-axis. Here the pressure of the gas is increased and this area under the curve is a PV diagram. And here the work done by the gas is negative. And third is when the volume of the gas it changes from V1 to V2 at constant pressure, there is pressure is constant and volume of the gas it changes from V1 to V2, then the curve is parallel to the volume axis as shown in figure. Here the pressure is constant and volume it changes from V1 to V2. Therefore, there is curve is parallel to the volume axis and work done is 0 because there is no any displacement. Okay. In this way, we can see the PV diagram and first law of thermodynamics. In next lecture, we see next point. Thank you.